Okay, so hi everyone. Welcome to this week's South American Geometry webinar. Um, as usual, if you wish to subscribe to our mailing list, you can send the word webinar to our email according to instructions on the chat. You might as well join our announcements WhatsApp group. Just receive announcements by following the link, also available on the chat. You can check our calendar for upcoming events on our webinar page, as well as check previously recorded talks on our YouTube channel. If you wish to add this recurring event to your Google agenda, you can click on this ridiculously long link, also available on the chat. Before I announce today's speakers, let me also make let's have a word of our sponsors, which is the Bridges Workshop Conference 2024. So if people are interested, this will be a conference on differential and algebraic geometry, reflecting our Bridges collaboration with France. All are welcome. Topics will include special geometries, gauge theory, geometric analysis, and similar things relating to theoretical physics as well. So please go and check. The link is here on the chat, and applications are open. This conference will be in lovely Corsica in France in late June, early July 2024. It'll be a week one with a summer school with courses for postdocs and young researchers and graduate students, and the second week will be a high-level international talk on aspects of differential and algebraic geometry, which are in close relation. So without further ado, let me introduce our fellow Brazilian based in Chile, Rayssa Caju from Universidade de Chile, telling us about constant Q-curvature metrics. So Rayssa, thank you. Can we do 50 minutes plus questions?
Okay, perfect.
Please go ahead.
Okay, so first of all, thank you very much to Enrique. Thank you very much, everyone, for this kind invitation. I'm very happy to contribute with a talk, to participate in the seminar. My goal today is to try to, in a way, can you hear me well? Is it?
Yes.
Yes,
Have
yes.
like
It's perfect.
Okay, no, perfect. So my purpose today is to try to talk about recent, more or less recent work, but undergoing project, because it's a big project, in collaboration with João Henrique Andrade from USP, São Paulo, which he is a postdoc, with João Marcos Duo, with Jess Ratzinger, and with Almir Silva Santos. Okay, so I will start with a little bit of introduction. So maybe back in the 60s, a little bit of history. In an attempt to solve the Poincare conjecture, there was a very famous problem that was proposed by the Japanese mathematician Hidehiko Yamabe, and he was in this sort of attempt to try to solve the Poincare conjecture. He was trying to modify the geometry of a given manifold, and he was trying in particular to modify the metric in order to find a new metric, in a way, a better metric for your manifold, which possibly could have constant scalar curvature. So this was the problem that was proposed. So Yamabe was trying to find in particular a conformal metric, a new conformal metric to the manifold who had constant scalar curvature, which means that the manifold would have a better shape, and maybe this would be a path to try to achieve to obtain in a certain way the Poincare conjecture. Okay, so here, just to explain, so the proposed problem was to try to find a conformal metric. So what it means, a conformal metric. So if you have your Riemannian manifold, we say that a new metric is conformal to the original one when both of the metrics are related by a positive function here, which means an angle preserving the two of the metrics, they preserve the same angles, they share the same angles, but they don't necessarily share lengths. Okay, so which means basically that the Yamabe problem can be reformulated, can be written as you are trying to find a new metric which has constant scalar curvature. Okay, so the magic and the highly good contribution of Yamabe at that time was to try to solve the problem was, look, we are trying to find a conformal metric to the original one. So let's try to write this conformal factor in a smart way, which means Yamabe found that it was very nice to try to write this conformal factor as u power to 4n minus 2. So he realized that there was a transformation law that the scalar curvature satisfied. So if you switched your metric, if you changed your metric in this way, you would have the new curvature equal to the old curvature, the Laplacian times the potence. So if you're trying to find a new solution where this here is constant, you would have that your problem is equivalent to try to solve an elliptic PDE with a critical exponent here. So you would start with this very geometric problem, and you would get this PDE problem in the end, the equivalence to try to solve, to find a positive solution for this problem. So, and here, there's this very nice part here. So this LG, which is the Beltrami Laplacian minus the curvature, this is called the conformal Laplacian, which means that this conformal Laplacian, this is called the conformal Laplacian because it also respects this conformal property that you are working with. So in a way, this equation respects the conformal structure of the problem, which makes this Yamabe problem a problem inside the area of conformal geometry. Okay, so a little bit of history. This is very well known, but I will try to summarize here. This problem was tackled first by Yamabe, and in '68, the mathematician Neil Trunge, he found a mistake in the proof. So it was later remedied by Trunge, by Aubin, and finally by Rick Shen in '84. And this was a very nice problem in the point of view of PDEs because it was one of the first PDEs with critical exponent to be fully solved. So it was a remarkable problem, both from the geometric point of view and both from the PDE point of view in a certain way. Okay, so the techniques they try to use and etc. to try to tackle this problem were variational techniques. But because this equation has this very particular exponent here, it was very hard to apply directly this kind of methods. Okay, so this is a little bit of history of the Yamabe problem. And after they solved fully this problem, Rick Shen, that was the mathematician who sort of closed the whole thing, together with Yao, they proposed a sort of a new version. So they were trying to look to the sphere, in particular the sphere, because it's always the model. So they are trying, look, do you think we can get to construct solutions of this problem in the sphere minus a set of points? For instance, geometrically, this would mean, do we think we can find a conformal metric which has constant scalar curvature, but now which is complete on the sphere minus this singular set? So this was a problem proposed by Shen and Yao. So we have some sort of singularity. We are passing from this compact initial setting to now a non-compact setting, and we are trying to find a metric that it's complete precisely on the sphere minus this singular set. So from the point of view of PDEs, this would be equivalent to find a smooth solution of our equation. But now we are trying to look for solutions, for positive solutions, who would explode in this singular set. Okay, so this is a little more complicated in some ways. Okay, so they proposed this problem in the case of the sphere, but it was a very natural thing to try to generalize this for any given manifold. So this is known as something called the singular Yamabe problem. So you start with sort of a manifold, you remove a singular set. So can you, given this compact manifold, can you find a new metric to the manifold, which is complete, and this, the completeness part is very important, which is complete and has constant scalar curvature. Okay, so in the case for this particular problem, this geometric problem is equivalent to try to find you a positive solution of this PDE, right? But that such that the U explodes on the singular set. And why is it important that the solution explodes in this singular set? To guarantee that when you take this metric here, this metric is complete and has constant positive scalar curvature. Okay, so this is sort of the new problem, a new version of the problem that people started to work. Okay, so they quickly, in a way, they quickly realize that the existence of solutions to this problem, the existence was related, connected directly with two things of your problem. The first thing that was equivalent to is the size of the singular set. Okay, so it depends on the dimension in certain ways. So your singular set is only points. Your singular set is composed by something that it has some dimension on it. So this was one of the first things that were relevant in order to try to tackle this kind of problem. And the second thing was the sign of the scalar curvature that you were starting with. So you had a manifold, a starting manifold, but this manifold had some scalar curvature. So you had to look at the sign. Okay, so the one of the first works that started to appear were due to Avils and McCohen in '88. So he noticed that if you have your sign to be negative, then to a solution exists, necessarily you have to have your dimension, here K is the dimension of your singular set, to be big. So if the sign of the scalar curvature is negative, you need this set to be big. So, and then with two other works, especially by Mazel and Parker in '96, they managed to solve the whole thing when the sign of the scalar curvature was positive and when the dimension was between 0, strict, and n-2/2. So here, this dimension is sort of the critical one. So if the scalar curvature is negative, solutions exist if and only if your dimension is big. And here, in these two works, if the scalar curvature is positive, solutions exist if and only if your dimension set is small. Okay, so this was related to this first part. So what people started to wonder, okay, yeah, you know how to deal with this problem when you have a singular formation that has some dimension. But I mean, what about when you are removing from your manifold only a finite set of points in a way, okay? So I mean, you can assume that, let's assume that we are working in the very basics with the case, for instance, of the sphere, a manifold which has constant scalar curvature, because we know how to solve the problem in the compact case. So if we are trying, for instance, working the sphere and removing a set of points, there were two constructions that were done in order to solve this problem. So there was a paper by Rick Shen in '88 in which he managed to construct, this is sort of the geometric representation of what I'm talking about. He managed to construct solutions to this problem, connecting necks and attaching bows in the singularities when your singular set in the case of the sphere has at least 2 points. Okay, so Rick Shen, he managed to do this, and later after, but his construction was a little bit complicated. So later after, there was a construction by Mazel and Packard, where he managed, they were a little bit more not as smart, but they managed to simplify the construction a little bit, and they attached what it's called the Delaunay ends in each of the singularities. So instead of attaching infinitely spheres, you were attaching surfaces in a way in each of the singularities, okay? So this was what was done for the case of the sphere, and of course, it is possible to do for a lot of manifolds. So there were 2 works by Bide after that, and by Almi Silva Santos, who works at UFS, that they managed to do this construction for several other manifolds, assuming some non-degeneracy of the metric. I will not enter in details, but I mean, it's for a lot of metrics that this condition holds, okay? So this is a little bit of the story regarding the part of the Yamabe problem, and when you bring this Yamabe problem to this sort of non-compact setting, okay? But now I will move a little, and I will try to talk about the thing that I came here to talk, and I came here to try to motivate you a little bit, which is this Q-curvature, okay? So what happened was similarly to the time that Shane was working in the ending of the Yamabe problem, and that conformal geometry was really growing in this time. In 1983, and Panades, he discovered a 4th order operator. It's a higher order operator, which had a conformal structure as well, which means I mentioned in the beginning of my talk that the conformal Laplacian had this conformal structure. So Panades discovered a higher order who also had some sort of transformation law that respected conformal structures, okay? So here was a little bit of the opposite. So he discovered the operator, and by looking closely to this operator, they realized that this operator was directly related to some sort of a new geometric quantity that it's called the Q-curvature. So here, this is some sort of a transformation law for dimension. You can see n greater than 5, but you also have some sort of transformation for lower dimensions, okay? So this operator here was related to this new geometric quantity that is called the Q-curvature. And what was fun about this quantity, I mean, I heard
Rayssa,
something. Any
yeah,
questions?
yeah. Why is it called Q?
Q?
Yeah.
You know, I have no idea
All right.
why they
It's a
call Q.
mystery.
It's
Okay.
for me, it's a mystery, and I will take a note of your question because I'm curious now.
You're curious.
Yeah,
Interesting
I'm
pun.
curious now. I'm very
All right.
curious why it's Q. No, it's a very good question. Thank you. No,
Okay.
okay.
Go for it.
So, okay, so they sort of try to define this new geometric quantity, and you can try to take a look at this curvature. When we start to looking to curvatures in higher dimensions, things start to get a little hazy. But what they realized was that in dimension 4, you could try to use the Chern-Gauss theorem, and you could verify that the quantity was related to the other characteristic of the manifold together with the Weyl tensor. So they sort of, the hope and the dream would be based on the information that they have at the time, that there was sort of an analogy between this quantity for dimension 4 and to the Gaussian curvature of a surface in dimension 2, which means they hoped that in dimension 4, this quantity could say a lot in the same way that the Gauss curvature tells us a lot in dimension 2. Okay, so this quantity, it was first worked in dimension 4, was extended for even dimensions by Branson, and after that there was a lot of works by Pfefferman, by Graham, by Branson as well, to try to get the expression that we have right now to the Q curvature, that in a few moments I will try to show to you. Okay, so one of the things that I was quite shocked when I started to take a look at this quantity is that if you, for instance, if you try to look for examples, if you take a look at the sphere has positive scalar curvature, right? And has also positive constant Q curvature with the standard metric. But if you look to the hyperbolic space, which has negative curvature, this has also positive Q curvature. Okay, so it's a quantity that it's a little different in some of the ways. So these examples are just curiosities and things to try to bring to the earth this quantity that I'm trying to motivate. Okay, so this is sort of the whole motivation. And since this quantity respects as well this conformal sort of transformation, naturally, based on the Yamabe problem, they try to take a look at the problem of prescribing the Q curvature of a determined surface, of a determined manifold. Okay, so they started to work with what it's called this Q curvature problem right now. So in the same way that we try to work with the Yamabe problem, if we have a compact Riemannian manifold, for instance, can we find a better metric in the way that this better metric is conformal to the original one and now has this constant Q curvature? Okay, so this is known as the Q curvature problem. So a little bit of history in dimension 4, especially there are a lot of works by Alice Cheng, by Paul Young, and by Jadili Malkiod especially. So these works were very important to try to solve this problem for dimension 4. Okay, so right now in this talk, I will really focus on the case n greater than 5. Okay, so in the case n greater than 5, again, using the same strategy as in the Yamabe problem, if we write our metric in this very special way as well, we could reduce this geometric problem in a way to the problem of finding a positive solution to this very beautiful PDE here, where this P is the Panay's operator, and here it's also a critical exponent. Okay, so now is the bad surprise. These are the current expressions of these two operators. Okay, so the Panay's operator is this very beautiful thing, which is the bi-Laplacian here, plus this divergence, plus here the Q curvature. And the Q curvature is given by this very beautiful expression. Okay, so what I try to focus is the fact that this is conformally invariant. This is an equation that behaves well, that transforms conformally, and it's fourth order. So besides trying to, of course, when you try to deal with computations, you have to look for these ugly expressions. But I mean, this is a well-behaved equation, which if you take a look and if you consider the metric here to be the simple one, this is simply the bi-Laplacian. Okay? Any questions? I heard something.
Yeah, I'm sorry. I want to make a little bit silly question, but
Oh, don't worry.
what's the geometric meaning of this Q curvature? So what do you mean? What do you understand by a manifold having constant Q curvature or even zero Q curvature? What's the insight behind this?
So this is the catch in a way. So especially in dimension 4, when you're trying to work with things that have sort of constant Q curvature, in some ways, you could say that your metric is Einstein. There are a lot of sort of rigidity results connecting this Q curvature quantity. Okay, so it's similar in a lot of ways to the scalar curvature, but I mean, you have some rigidity results around the whole quantity, but it's a little bit hard to work with it. I don't know if I make sense or not. So what I'm trying to say is that there are a lot of results that give topological properties based on the constancy of this quantity, on the constancy of this integral. So this says a lot about the manifold, especially in some types of dimensions.
Nice. Okay. Thank you.
Okay. No, don't worry. It's a little bit more abstract, so it's a little bit ugly. But I mean, there is a survey. There are two surveys that really specify this. One is by Alice Cheng. No, it's both by Alice Cheng, and I can share in the end if you are curious about this. Okay.
I just
All
did.
right.
It's on the chat. So
It's on the chat?
what is Q-curvature by Alice Chang, Michael Eastwood, Orson Yang? Yeah, this is a great short text about Q-curvature. You can read in one go, just after the talk. And it's really well written. All the results, basic stuff is there. This is the one you're going to recommend?
Yes, precisely this one. Precisely.
Yeah, I
Thank
really
you very
like
much.
this one. So yeah, cool. Yeah, it's on the chat. Please go on.
No, it's precisely this one. There is a longer one that is also by Alice Cheng, the one that I like the most is this one. What is Q curvature? It's a very pretty one.
Yeah.
Okay, thank you. Sorry, I cannot see you, so it's a little weird, but okay. Okay, so what are the main difficulties here compared to the Yamabe problem? I mean, you can say to me, okay, this is only a 4/4 version of this problem. You're doing the same thing. So this is a variational problem, and here is the whole catch. There is a lack of maximum principle to this operator since it's a 4/4. So this was the main challenge when people were trying to deal with this. And there is a very famous paper, especially by there are some results, but there is a very famous one that is by Gursky and Malchiodi, that they managed to find sort of a maximum principle to help to deal with this problem. Okay. All right. So here I will move a little bit to the case that I'm really interested, that is this non-compact case, this singular setting. So you can try to pose the same problem in this non-compact case. So the question would be, now given a compact manifold M, we want to find a new metric, a conformal metric, which is complete in M minus the singular set and has constant Q curvature. Okay, so here three things now that are relevant. So the first one is the sign of the scalar curvature. The second one is the sign of the Q curvature. And the third one, finally, is the dimension of the singular set. Okay, so I will focus on the rest of the talk when the dimension of this X is only points. I will be removing only a finite quantity of points. But there is a very nice work by Hyder and Sayer that works with this set when the dimension is a little bit higher. Okay, so this is what I want to focus. What happens when the singular set is only a finite amount of points? We are removing a finite number of points. So the theorem that we managed to prove was that when we start with a Riemannian manifold, and here I will be assuming that this manifold has constant Q curvature. And you can ask me, why are you assuming something that you want to prove? Because I don't want to prove only that my new manifold has constant Q curvature. I want to prove that this new manifold has constant Q curvature and is complete. And I know how to solve the problem in the compact case. So this is fine. This part here is fine because we are very interested in trying to solve the completeness. So if my metric satisfies some hypothesis that I'll be hiding here, we can find a family, a one parameter family of solutions to this problem. So we managed to solve the singular Q-curvature problem under some two conditions. These are the important conditions under some two conditions for the manifold. Okay, so I will try to be very brief about this part. What is the sort of the general idea from the PDE point of view to try to solve this problem? So the general idea is to try to use a fixed point method. So I don't know what is the solution that I'm looking for, but hopefully I know a very good approximation. So I know I use zero, that is a very good approximation. So if I'm trying to solve this PDE here, that I will write this H only to write the operator. If I'm trying to solve this PDE, I can try to linearize this whole thing. Okay, so if I linearize this, and since U0 is a good approximation, this part here should be almost zero, very close to zero, because this is almost a solution. This is a linear operator, this is a remaining term. Okay, so this is majorly the idea that we are trying to do. So if we study this linearized operator, and this linearized operator has a right inverse, then we can reduce this problem to try to solve a fixed point problem. Okay, so this is the whole idea from the PDE point of view. But I mean, here is the catch. Here is the part where it gets a little bit complicated for us, because the notion here of good approximation is very different if we are near the singularity or if we are far away from the singularity. So here is the magic. What we try to do is the following. We try, no. Okay, so let's try to build a solution near the singularity. Let's try to build a solution in the complement of the singularity, and let's pray that we can find enough parameters, enough variables that we will glue both the solutions together, and this will be a solution for the whole thing. Okay, so this is sort of the idea. So here I made sure that it's very important that we take a look and what is the model, what is the good approximation. So there was a work of our collaborator from 2020 that indicated who are the good approximations. They also call here Delaunay solutions. So the Delaunay solutions are simply the solutions of this for the equation here. Okay, in the Euclidean space minus zero. These are our models. But I mean, we have the models, we don't know anything about the models, okay? We can have a solution, but we don't know anything about the solution. So the other thing that happened in the same year was that there was a work by Frank and Koenig that classified the solutions of this equation. So they told us, look, the local models are like this. They depend on two parameters. They depend on an epsilon, and they depend on a period. So the surprising thing here was that even in four dimensions, these solutions only depend on two parameters. Okay, so from the geometric point of view, what would this mean? So this here would be the local models, the Delaunay solutions in a way, that also depend on a parameter, on an epsilon, which is this neck here, and that depend on a period, okay? So these are our local models that we are trying to glue very close to the singular point here, okay? Let's pick up one point, only to exemplify, okay? So we are trying to glue this here. So, okay, you have to try to modify near the singularity your initial metric in order to create something here that will approximate this neck. So the idea is to perturb the original metric on the outside by a green function at the pole P and try to get parameters that will make this glue. So that is the PDE idea, and this exemplifies what is happening from the geometric perspective. Okay, so here, if I have some time, I have more or less 10 minutes. here is the technical part. Here is the technical part. I can jump this part. I can jump this part because I already explained the ideas. But this part is only important to see where the ugly hypotheses that we put on the metric, they come. So we divided the problem in 3 parts, right? Interior analysis to try to build a solution near the singularity, to try to build a solution in the complement of the singularity, and to try to glue, right? So for the first part, we are trying to construct solutions for this problem in a small ball near the singularity that explode on the point. So we applied our strategy. We linearized the problem and we reduced the problem to a linear equation. Okay, we reduced the problem to a linear equation, and the mission is to try to understand the linearized operator. So when you linearize, you get the metric, original metric. We don't want to work with this metric. We want to work with a simple one. We sum these terms, we sum 0 in the equation, and we try to understand this simple linearized operator. So is there any good space in which this operator admits a right inverse? Yes, there is, and it's weighted other spaces. So this part, I will not enter in details at all, but I mean, what I want to exemplify here, that this is where the first hypothesis is coming, is that if we are trying to solve this, again, we would have that the linearized operator, it's equal to some expansion, right? So in order to reduce this equation to a fixed point problem, I have to have that this rest here, this right-hand side, belongs to the domain of my right inverse. So for dimensions 5, 6, and 7, I'm okay. This is true. For dimension greater than 8, we need to assume some hypothesis. And this hypothesis that the Weyl tensor at the point is vanishes up to certain order. Okay, so this is the hypothesis that we assume only for dimension greater than 8. This is a dream to try to remove this hypothesis both from the scalar case, both from the Q-curvature case, but we didn't manage to do this. Okay, but I mean, this is only for dimension greater than 8. And this is related actually to a conjecture which is called Weyl vanishing conjecture. That's why we put this hypothesis. So it's related to some decays, and these are very technical things that I will not be talking right now. Okay, so with this, we solve the problem on the interior. What about the problem on the exterior? So like I said, in the exterior, what we do is we modify our origin metric for a green function at the pole, but we need to modify this. We need to assume the second hypothesis here on the metric. In order to solve the problem, we need to assume that the metric is non-degenerate. Okay, so for those who are curious, we have, if we assume that this metric is non-degenerate, we will have that this green function exists, and then we can use it to try to find the fixed point. So this is sort of the technical non-degeneracy hypothesis, but the important thing here is that they should be generic, okay? So several metrics should satisfy this condition, okay? So with this, this is the technical part, okay? So with this, we have an interior solution, we have an exterior solution, and we pray that we can glue. But in order to glue this, you have to solve some sort of system, and you also reduce this to a fixed point argument, okay? And to solve a system with that many equations, you need to introduce along the way several variables, okay? So I put it here as a matter of curiosity, that this is why the gluing constructions are so complicated sometimes, but this is sort of the way that we do. We construct something in the interior, we construct something in the exterior, and we have to introduce enough variables to make this system here solvable. So the things that we are trying to to construct blue blue. Okay, so finally, this is our main result. So we saw the main result, summarizing, is that we solved the singular Q-curvature problem when our initial metric G is non-degenerate, and when in dimension greater than 8, the Weyl tensor vanishes at the point, only at the singular point. Okay, so this was our main result, and we are still trying to tackle several problems related to there. There are a lot of things that are still open. Okay, so for instance, one of the interesting problems is that, okay, we construct a family of solutions. There are other families of solutions that you can construct for this problem. For instance, I mentioned at the beginning that there are two different constructions of the case of the sphere. One by Rick-Shane, that you glue spheres, and the other one by Mazeu-Packard, that you glue these Delaunay solutions. So can you try to understand all the solutions? Can you try to take a look at the moduli space? So for instance, here, what happens when your scalar curvature is negative at the beginning, when your Q curvature that you're trying to prescribe is less or equal to 0? So there are a lot of questions that we are still trying to talk about to try to solve. And here it's for the geometers, really the geometers, is that there is an analogy. It's more a curiosity that I will end my talk with this. So there is an analogy between constant scalar curvature metrics and CMC surfaces, which means that it's very fun to see the papers that you can see always when there is a construction for one, there is a construction for the other one, using more or less the same techniques, and everything works in the same way, which is fun because one of the problems, the nature of the problem is extrinsic, and the other one, the nature is intrinsic. Okay, so one of the curiosities that we have, okay, we are constructing things with constant Q curvature. Do we have any sort of analogy of this quantity with some kind of other surface which has this relation here? So this is sort of a curiosity that we had that we don't know if it holds or not. So and we are still trying to evaluate. So this is more or less what I had to talk today. Thank you very much for your attention. And if you have any questions, I'll be happy to answer.
All right. Thank you.
Let me see you.
Okay. I'll let you see me. Thank you so much, Rayssa. Do you have questions for Rayssa? There's lots of clapping going on. Yeah, excellent. Are there any questions or comments? If you want to ask a question, you can click on the little hand at the bottom of the screen, if you're not familiar with Google Meet. Well, yes?
So, Rayssa, do you know how this Q curvature behaves in homogeneous spaces and manifolds that have some symmetries?
Like in the sphere, for instance?
Yes. Because this Q curvature was introduced by Tom Branson, yeah, right?
Yes.
And Tom Branson made some things on spheres and homogeneous manifolds as well. So I guess that he could say something about this Q curvature also for homogeneous spaces. Do you know something about it?
Okay, so in the sphere, the Q curvature, the quantity is constant. That for sure. But I know that there's a famous result by Gursky, I guess, which sort of has a criterion to know if something is a sphere based on the Q curvature. So under some conditions, I think it's positivity of the conformal Laplacian or something like this, you would have that if the integral of the Q curvature is the number, I guess it's 16 pi squared. I'm not sure. So if it's something like this, if the equality holds, then your manifold has to be a sphere.
I
So-
suppose Luisa's question goes, if your manifold is a quotient of Lie groups, for instance, right?
Okay.
And then if you pose, I suppose the question would be, if you pose the symmetry to the Q curvature, does the problem of constant Q curvature reduce in some sense to a simpler equation, right? Because you have a very hard PDE, and the standard question on a homogeneous space is, can you somehow reduce this hard PDE to a no DE if you're looking at invariant quantities on this quotient, right, under the symmetry. So do you know that people have been studying sort of Q curvature on the symmetries?
No, I only know. I only know that in Einstein manifolds, in particular, the Q curvature has a sort of a decomposition that makes it easier to work on. This particular case, I don't know. I can try to take a look, but I don't know. But it should be valid, I think. Yeah, but I don't know.
Okay. Yeah, so we could have a look at this.
I always take note of
knows
the question.
Luis knows this question, and he asks it regardless of the context, right? So that's excellent. I have a question as well. So the actual computation of Q curvature depends only on the Riemannian curvature tensor and its traces, right? It's various,
Yeah.
right? So Ricci and then scalar, and it's Laplacian and rest of it, right?
The Schouten tensor.
Indeed, the
Correct.
Schouten tensor.
The
And now, of course, if you vary a metric, the Riemannian metric, or if you vary it as a conformal class, then we understand how the Q curvature varies. There's a sort of subtler way to pose a variation, right? Because you could, when you vary the metric, in particular, you vary the Levitivity connection, which is the metric compatible connection on the tangent bundle.
Okay.
Right? But you could vary the Levitivity connection in a non-metric way, right? And you could consider the general problem of starting with a Levitivity connection of a metric G, and then varying it, just deforming it by a SON valued one form, I guess.
Okay.
Right? You could vary this connection in a way that is not metric.
Okay.
But this still gives you a variational problem on the Q curvature now, because you could ask, are there any such variations such that the Q curvature, for instance, remains constant for non-metric connections? For metric connections, in the compact case, you just told us this problem is well understood. But what about sort of more general variations? So, do you know that anyone has been doing this? It's a sort of a Yang-Mills approach to Q curvature, I suppose.
Okay.
As a variational problem on the connection, the curvature of which you use to define the Q curvature, right?
Okay. Okay. No, I mean, for instance, I can tell you, for instance, this singular problem that we are working on, people started working on 2020.
Mm-hmm.
So these are very recent. And there are still cases that are open even on the compact setting. So in my knowledge, I don't know if there is some sort of a Yang-Mills approach, let's say in this way, a Yang-Mills type problem for this. But I mean, I can definitely try to take a look. It's a very interesting question.
The reason why I think the two issues are maybe perhaps related is that even if you don't consider the singular problem for a minute, even if you just consider the smooth problem, right? Can you still, nonetheless, on a closed manifold, do we understand this sort of variational approach where the variation is on the connection on the tangent bundle in a sort of non-metric way? But assuming we did understand that, and we could maybe understand the special deformations or sort of special connections on the tangent bundle that still give you constant Q curvature, you could then have a bubbling problem associated to these fellows. So in the sequence of these guys, does that form a singularity along some locus? And then this would relate to the singular version of the problem in a sort of more or less transparent way. So even in the sort of non-singular case, my understanding is that the singular case is some sort of limit, a sort of compact. It's a sort of boundary element in a theory of the non-singular guys anyway. So they would, they wouldn't be related immediately, but I think they would be related in a little while, just around the corner.
Okay.
So, right, because even if you had the smooth, a good understanding of the smooth objects, then you could still look at sequences of those, and they would probably bubble along sort of singular loci, which would be related to the singular study.
To the singular.
Right? So, or conversely, take one of the cases you already understand, right? And we could ask the converse question: is this the limit of a sequence of smooth data, which are Q-curvature constant?
Okay.
Right. So can they emerge? Right. Do these sort of emerge as limiting situations? Are these the bubbling loci of sequences of a smooth data? So you could ask it both ways. Now, and these questions may be complete nonsense because I'm importing them from sort of gauge theory inside, but it appears, I don't know, it appears somewhat natural in this context. So I was just yeah.
I think that this was similar actually to a question that I think one of my collaborators was talking to Rick, and he was posing something similar to this, sort of a limiting approach to this.
Oh, if Rick asked this, then it must be a good question.
No. No, but he was asking something. He was asking something like this, sort of a limiting part, the converse of your first question.
Yeah.
No, okay. No, I'm full of notes here because I'm a PDE person learning some geometry now, and it's always good to me to sort of import these questions that are natural for people who really work with geometry. So thank you very much.
All right. Yeah, I'm a non-PDE person learning geometry now, so you have an edge on me. Excellent. Well, if you feel like discussing this, or whenever you come home for a break, do stop by in Campinas and let's have a chat.
It will be my pleasure.
Cheers. Do we have any more questions or comments for Rayssa? Well, if not, then let's thank the speaker again. You can do it by actual clapping, or now you can use these nice devices. Look at that. Yeah.
Very much.
Yeah, we can use these buttons now. Okay.
Love things. Okay. Thank you very much for the invitation.
Thank you,
Cheers,
Rayssa.
that was great.